Okay, so when I say Math Olympiad, what do you picture? Probably some brilliant high schoolers, right? Scrawling these impossible equations on a blackboard? But what if I told you we're talking about a 6-year-old, a first grader? What on earth does advanced math even mean for them? Well, today, we're going to crack that open and see what's really inside one of these first-grade math competitions.
All right, to really get this, let's just jump right in at the deep end. We're going to start with a problem from a sample final exam. And trust me, it looks less like a math question and a whole lot more like a puzzle you'd find in some kind of adventure game.
So here it is. An insect is inside an apple. Which path should it take to get out? And get this is a math question for a first grader. So how are they supposed to solve this? I mean, really, how does a kid who's just getting the hang of counting even start to tackle this thing? It seems impossible, right? But here's the twist. The answer has almost nothing to do with complex calculations. It's all about learning a whole new way of seeing.
So, to figure out how a first grader can solve that apple problem, we've got to rewind. We have to go all the way back to the beginning and look at the actual building blocks they're being taught. And let me tell you, they are probably not what you're expecting.
Okay, so on the left, that's what we all pretty much think of as first grade math, right? Fast arithmetic, simple counting, 2 + 2 = 4. But what this Olympiad curriculum is all about, it's a completely different universe. Over on the right, you can see it's all about stuff like spatial relationships, the properties of solid shapes, and recognizing patterns. See the difference? It's less about how many and way more about where, what, and what comes next.
You know, the best way to wrap your head around this is to think of it like they're learning a new language. Seriously, it's a vocabulary built from the ground up to describe the world with logical precision.
And just look at how basic these words are. This is the absolute core vocabulary. I mean, before you can even dream of tackling complex geometry, you need a super precise way to say where something is. Is it on the box or in the box? It sounds simple, but this is the first building block. It's the groundwork for literally everything, from reading a map to imagining how a car engine fits together.
And this isn't just fluffy stuff. They test this vocabulary directly, very systematically. So for example, a kid might get asked to just point out the picture where the mouse is under the table. It's a really simple question, sure, but think about what it's testing. It's not testing counting, it's testing their understanding of a spatial concept.
And then bam, another question. This time, they might have to identify what's outside the house versus what's inside. Every single one of these questions forces a child to really look at a scene and apply a specific logical word to it.
And this one really brings it home. It shows that knowing the difference between in, on, and under is a real testable skill. It's just as crucial as knowing that 2 + 2 is 4. This spatial language, this is the foundation for everything else that's coming.
Okay, so once a student can describe where an object is, the curriculum moves on to teaching them to describe what it is. And that means a whole new set of vocabulary: faces, edges, and vertices. We're talking about breaking an object down into its geometric parts.
This is a perfect example of how they use that new vocabulary. You literally can't answer this question, how many edges does this figure have, unless you know what an edge is, and you can patiently, systematically count them all. It's all about careful observation and applying a definition. That's it.
And here, they kick it up a notch. It's not just about pointing out properties anymore, it's about comparing them. The student has to look at 2 different shapes, remember the definition of vertices, count them for each shape, and then make a comparison. That's a multi-step logical process right there.
So, okay, we've got a language for location, a language for shapes, but there's one more piece to this puzzle. And this one is about completely rethinking what a number even is.
It's all about seeing numbers in a totally new way. Instead of just seeing the number 23 as, well, 23, students are taught to see it as a collection of groups. This whole idea of tens and ones is the absolute bedrock of place value, which, believe it or not, is a surprisingly abstract concept for a little kid to get. So yeah, the number 23 isn't just 23. It's 2 groups of 10, with 3 single ones left over. Teaching it this way helps kids understand why our number system works the way it does, instead of just memorizing a bunch of rules.
And finally, let's talk about patterns. Solving a pattern problem isn't some magic flash of insight. It's actually a super methodical process. Step 1, you identify the pieces, the shapes, and the sequence. Step 2, you look closely and figure out the repeating order.
And step 3, you use that logic to predict what has to come next. It's pure logical deduction.
So when you start to put all of this together, the spatial words, the properties of shapes, the structure of numbers, and recognizing patterns, you start to see the bigger picture emerge.
And this, right here, is the key takeaway. The whole point of that apple problem isn't just about finding the right path out. No way. It's about giving a child a mental toolkit, a framework to approach any complex, unfamiliar problem and know how to break it down into small, logical, manageable steps.
These are the real skills being built here. We're talking spatial reasoning, logical deduction, pattern recognition. This curriculum is building the foundation for scientific and mathematical thought. It's about teaching kids how to think, not just what to know. Every single problem we've looked at today is like a workout for one of these mental muscles.
And ultimately, this is the whole philosophy in a nutshell. It's not about knowing the answer, it's about learning how to see the question.
So that kind of leaves us with one last big question. What happens when we teach 6-year-olds to think like mathematicians from day one? What are the long-term effects of training the brain to work this way so early on? What happens when a whole generation learns to see the world not just as a bunch of stuff, but as a beautiful system of patterns and logical relationships? It's a pretty fascinating thing to think about.